Finally, we'll look at some applications. This one is to find the shaded area of the concentric circles pictured below. In order to do that, we need to know, how do you find the area of a circle? So if you've taken geometry, you may recall that the area of a circle of radius r is given by well, let's depict it first. So the radius is the distance from the inside or the center of the circle to the edge of the circle. So r. Then we could say that the area of such a circle is pi times r squared, where pi is a special constant that we can approximate with 3.14. All right. So this picture here is saying the inside circle has radius x, and this line from the center to the edge of this circle is depicting that the outside circle radius is x plus 2. So the shaded area conceptually is the larger area minus the smaller area. So shaded area is area of outside circle minus area of inside circle. So using this formula at a equals pi r squared, we get shaded area equals, well, the area of the outside circle is its radius x plus 2 squared times pi. So it's pi times x plus 2 squared. I missed my 2. X plus 2 quantity squared. So the area of the inside circle would be pi times x squared. All right, so substituting those in, we get shaded area is equal to pi times x plus 2 squared minus pi x squared. So that's pi times x plus 2 times x plus 2 minus pi x squared. So the pi's you want to treat like constants. All right. Then we're going to multiply this polynomial into here, into here. So we have pi times x times x plus 2. But this pi is being multiplied to this entire product. So we might as well group these together. We can put extra parentheses in here. So the pi will leave for last. And then we have x plus 2 times x. And then quantity x plus 2 times 2. That's the same thing as plus 2 times x plus 2. And then minus pi x squared. Now we have pi times, here we distribute in and get x squared plus 2x. Here we distribute in and get 2x plus 4. You don't want to distribute that pi in until all the like terms have been combined. We have 2x, we have two like terms, 2x and 2x. We have pi outside, and then x squared. Combining here, we get 4x, and then plus 4. And then minus pi x squared. Now we'll distribute the pi through. And you get pi x squared plus pi times 4x, just write 4 pi x. So that's 4 times pi times x. Just write 4 pi x. And then pi times 4, do 4 pi. 4 times pi. Then minus pi x squared. And notice that these are like terms. And they cancel because they have additive inverses for coefficients pi and negative pi. So cancels. And we have 4 pi x plus 4 pi. What is that? Well, depending on what x is, that's this shaded area here. So, sort of the, think like a donut. Like that. So depending on what x is, that gives us this distance. And x plus 2, that gives us this outer radius. This expression here tells us the area of the shaded area. All right. So we are going to do this you try it. So suppose that the demand for gadgets is given by this function. X equals 320 minus 1.5p. So x as a function of p, where x is demand and p is the unit price, is 320 minus 1.5p. Right. Use the graphing calculator to determine the unit price a retailer should charge for gadgets so that her revenue from sales equals $12,000. Well, here's just a fact from economics. Revenue is equal to demand times price. So as you change the price, the demand will go up or down. So revenue as a function of price, we will symbolize with R of P. All right. So R of P is X of P times P. Thus, in our case, we have revenue as a function of price is X of P is 320 minus 1.5P. So we get 320 minus 1.5P, and then times P. So we want to distribute that P on the outside of the parentheses into each term. This P distributes to here and to here, since we're on the right. And I'm pulling up the graphing calculator. We're going to need it for this problem. And so we have 320P minus 1.5P squared. Now, to find P when revenue is $12,000, which means what price do you have to charge in order to collect $12,000 from all the consumers who wish to buy your product at that price? To find P when revenue is $12,000, find the intersection of y equals your function 320p minus 1.5 p squared, but since you'll be putting it into the calculator, your independent variables will use x. So y equals 320x minus 1.5 squared, and y equals 12,000. So the 320x minus 1.5 squared comes from here, and the 12,000 comes from here. So go to your TI. And type those in. So y equals, clear out any equations you might have. And then we had 320p, but our variable is x on the calculator, minus 1.5p, but x here, squared. And then whatever the revenue is. So you need to build a revenue function. This is your revenue function, and then take the specific revenue you're given, which is a constant, and graph them. All right. So we know we need 12,000 on the graph. So go to Window, and revenue is on the y-axis. So y minimum can be set at 0. And because we're not interested in negative revenue. And then y maximum can be set at a little bit above 12,000. So how about 12,500? And then to get, divide that by 10, and you get 12,000 or 1,250. Dividing it by 10, since it goes from 0 to this number, would give us 10 tick marks on the x-axis. So change your scale to 1,000 is reasonable. We'll get about 12. And then X max, we're not interested in negative prices, paying people to take the goods, so 0. And we didn't see the curve come down on the other side, so maybe we can expand this out to 100. Since it was at 60, let's get it to 100, then we can use our powers of 10 trick. And make this here a 10. Let's see what this gets us. Graph. All right, we're starting to see some curvature there, and there's our revenue line. We can sort of hypothesize that the curve will do something like this, maybe, because it's starting to curve back towards the horizontal. So we don't need to come up so far, but we're definitely still going to have to go out this way. About twice as far, it looks like. From we can kind of guess that the curve kind of curves up to horizontal somewhere about here. So maybe twice as far on X, and at least 5,000 more on Y. So since it's at 12,500, let's go with 20,000, a good number. 2,0,0,0. And then 200 here. So this, our X max is 200, and then let's double our scaling. So we'll make X scaling 20. Let's see what this looks like. All right, well, that's nice. We have the intersection of both points of intersection for our curves. So next we go to recall second and calc. So hit the trace button and then go to intersect. Enter. First curve, hit enter. Second curve, enter. Since those are the only two curves we have. And then move the cursor over to your guess for the point of intersection and hit enter. So the intersection is 48.548. Let's round that up to $48.55. All right, so right here we have 12,000. Then here we have 48.548014. So a price of $48.55 results in a revenue of $12,000. Okay. And you could use this curve to figure out what would be the optimum price in order to generate the most revenue, which we will do now. And we'll call this B, part B. What price maximizes revenue? Coming back to our TI. So our revenue curve is in blue. So we want to find the maximum. So we go to second, calc, and then down to maximum, and hit enter. Now move the arrow over to the vertex of the quadratic, of this graph of our quadratic function. Okay, and then you want to be a little bit to the left, so that looks good, and a little bit to the right. Well, that's more than enough. We can come back in a little bit, where the pixels sort of take a step up on either side. And then the guess, well, somewhere in the middle. That looks good. Enter. So the maximum is 100. Well, the maximum occurs at a price of $166. $106.66. And then the revenue at that price is $17,000.66. So $17,066.67. Clearly, I'm not very good with money. All right. So we see here that a unit price of $106.67 maximizes revenue. So it generates a maximum revenue of $17,000. $17,066.67. And that concludes this lecture.